100 billion. That is how many stars are in the Milky Way. Not approximately, not roughly. The best current estimates, derived from the combined mass of the galaxy, its stellar density profiles, and direct star counts in surveyed regions, converge on a number somewhere between 100 and 400 billion individual stars orbiting the galactic center in a flattened disk roughly 100,000 light-years across. Most people have heard this number, but here is what that number does not tell you. And this is the part that changes everything if you let it. Many have nodded at it. Some have genuinely tried to sit with it. And for most of them, the number has the satisfying completeness of something understood. The Milky Way, 100 billion stars. Big. Moving on. The Milky Way is one galaxy. The observable universe contains roughly 2 trillion of them, not 2 trillion stars. 2 trillion galaxies, each containing somewhere between a few billion and a few trillion stars of their own. The observable universe is not a neighborhood with a very large population. It is a structure of incomprehensible complexity, containing more individual stars than there are grains of sand on every beach and desert on Earth, multiplied by a factor of several hundred. It is not waiting to be reached by better telescopes or more sensitive instruments. It is hidden from us permanently, structurally, by the same physics that made the universe habitable in the first place. And here is the thing. The 2 trillion galaxies are not the universe. They are the fraction of the universe that the laws of physics permit us to see. What lies beyond the boundary of what we can observe is not empty. It is not featureless. The mechanism that solved the deepest problems in early cosmology also guaranteed that most of reality would be beyond the reach of any signal, any observation, any causal contact whatsoever. Get comfortable. Hit subscribe if this is your first time here. We are going to follow this all the way to the edge and then past it as far as the equations allow. The number that should terrify you. Deep in the data returned by the Planck satellite, the most precise mapping instrument ever pointed at the cosmic microwave background, there is a value that physicists treat with a reverence bordering on unease. It is called omega, and it describes the overall geometry of the universe. Not the geometry of a particular galaxy cluster, not the local curvature near a massive object. The geometry of space itself at the largest scale physics can measure. Omega is defined as the ratio of the actual density of the universe to the critical density, the specific density at which the universe is geometrically flat. An omega of exactly 1 means flat. When Planck returned its measurements, it found omega equal to 1.000, with an uncertainty of plus or minus 0.005. The universe is flat, not approximately flat, not flat within experimental noise. An omega greater than 1 means positively curved, like the surface of a sphere. An omega less than 1 means negatively curved, like a saddle. Flat to within 0.5%, measured across the entire observable sphere, across 93 billion light-years of space in every direction. Before you set that aside as a technical detail, sit with what it actually implies. Flatness in the evolution equations of the universe is not a stable equilibrium. It is an unstable one. A universe that starts with omega slightly above 1 does not stay near 1. It evolves away from it, curving more and more strongly until gravity wins and space collapses back inward. The window between these two catastrophes is not just narrow. It is precise to a degree that has no analogy in any other physical measurement. A universe that starts with omega slightly below 1 evolves away from flatness in the opposite direction, expanding so aggressively that matter never has time to clump together into structure. Either way, you do not get stars, you do not get planets, you do not get chemistry, you do not get anyone to notice the flatness problem in the first place. To produce the flatness we observe today, the value of omega in the first instant of the universe, at the Planck time of 10 to the negative 43rd seconds, had to be equal to 1 to within 1 part in 10 to the 62nd power. Write that denominator out. 10 followed by 61 zeros. That is the precision with which the initial conditions had to be calibrated. Any deviation larger than 1 part in that number, and the universe either collapses in a few 100,000 years or expands into featureless void long before a single star ignites. This is the flatness problem. And calling it a problem is an understatement that the name has made comfortable. It is not a puzzle about measurements being slightly off. It is a question about why the universe exists in the form it does, rather than one of the overwhelming majority of forms in which it would have been uninhabitable. Physicists did not accept this precision as a given and move on. They looked for a mechanism that could produce it. And what they found, what cosmology has been living with ever since, is an answer so extreme that it resolves every tension in the problem while creating a new and even stranger one. It is called inflation. And once you understand what inflation actually does, the universe you thought you lived in begins to look very different. Inflation is not the ordinary expansion of the universe that has been going on for 13.8 billion years. The expansion that solved everything. That expansion is gentle by comparison. Inflation is a period of exponential growth that cosmologists believe occurred in the very early universe, between roughly 10 to the negative 36th and 10 to the negative 32nd seconds after the beginning. A window of time so brief that expressing it in any human unit produces a number that lands nowhere meaningful in the imagination. During this window, space expanded by a factor of at least 10 to the 26th. Some models predict considerably more. To translate that number into something with any human texture, if you took a single proton, already so small that millions of them stacked side by side would not span the width of a human hair, and inflated it by the factor inflation applied to the universe, the resulting object would be larger than the entire observable universe we can see today. The expansion was not a movement of matter through space. It was a growth of space itself. The fabric of the universe stretched in every direction simultaneously, exponentially, without limit, without center, and without anything resembling ordinary physical process. What inflation does to the flatness problem is elegant and brutal. Imagine standing on the surface of a small sphere. The curvature is obvious. The horizon is close. The surface visibly curves away in every direction. Now, inflate that sphere by a factor large enough that its radius exceeds the observable universe. From any point on the surface, the curvature would be completely undetectable. The sphere is still curved, but the segment you can observe is so small relative to the whole that it appears flat to any measurement you could make. Inflation takes whatever curvature the early universe had, regardless of its initial value, and dilutes it below the threshold of detection. The flatness we measure today does not require a precisely calibrated beginning. It requires inflation to have occurred. This is why the flatness problem is not really a problem if inflation happened. Inflation solves it automatically, without fine-tuning, without any special initial conditions. Any universe that undergoes sufficient inflation ends up looking flat from the inside. They are separated by more distance than any signal could have crossed in the age of the universe at the time the background was produced. The horizon problem is one. The cosmic microwave background is uniform in temperature to 1 part in 100,000 across the entire sky, including regions that in standard Big Bang cosmology could never have been in causal contact. How can regions that never interacted have the same temperature? Inflation answers this by proposing that the entire observable universe expanded from a region so tiny that it had time to reach thermal equilibrium before inflation stretched it beyond causal contact. The uniformity was established before the separation occurred. The monopole problem is the third. Grand unified theories predict that exotic particles called magnetic monopoles should have been produced in enormous quantities in the hot early universe. 3 independent problems. 1 mechanism. A single period of early exponential expansion resolves all 3 simultaneously without requiring separate solutions. But there is a cost, and the cost is the hidden universe. This kind of convergence is precisely what physicists mean when they say a theory is compelling. It is not just that inflation fits the data, it is that it fits multiple independent pieces of data in a unified way that no alternative framework has matched. What inflation took with it, when inflation stretched the universe by a factor of at least 10 to the 26th, it did not stop neatly at the edge of what would eventually become the observable universe. It stretched everything, regions of space that before inflation were in causal contact with our region, close enough that light could have crossed between them, were pushed beyond any distance that light could have crossed in the entire subsequent history of the universe. Those regions are gone from our sky, not because they ceased to exist, not because their light is being blocked, because the expansion placed them so far away that no signal traveling at the speed of light has had sufficient time to reach us, and in a universe still expanding, no signal ever will. The observable universe, the 2 trillion galaxy sphere 93 billion light-years across, is not the universe. It is the fraction of the universe from which light has had time to reach us since the moment the plasma cleared and photons became free to travel. The rest of the universe, the overwhelming majority of it, is beyond what cosmologists call the particle horizon. It is causally disconnected from us, not distant in the way that a remote galaxy is distant, not beyond our instruments, but in principle reachable, but genuinely and permanently inaccessible. No measurement, no signal, no probe, no photon, no gravitational wave originating beyond that boundary will ever reach us. How large is the actual universe? The honest answer is that we do not know, because we cannot measure what we cannot observe. But we can set a lower bound. In 2011, 3 cosmologists, Mihran Vardanyan, Roberto Trotta, and Joseph Silk, published a Bayesian analysis working from the Planck data and asking what minimum size the actual universe must be to be consistent with the observed flatness. Their result was that the actual universe must have a radius at least 251 times the radius of the observable sphere. 251. That gives a volume roughly 15 million times larger than everything we can see, and that is the minimum. The conservative number derived from the simplest inflationary models. Many inflationary scenarios predict far larger expansions, pushing the actual universe to scales where even the word large begins to fail. 2 trillion galaxies in the observable universe. Multiply by 15 million. The number of galaxies in the actual universe under this conservative lower bound is roughly 32 sextillion. 32 followed by 21 zeros. Every single one of them out of reach. Not because our telescopes are not good enough, not because the universe is opaque, because inflation put them there, beyond a boundary defined by the laws of physics rather than the limits of technology. This is the central fact from which everything else in this story follows. The universe that is hidden from us is not featureless. It is not empty. It formed from the same initial conditions, the same inflationary perturbations, the same quantum fluctuations stretched to cosmic scales. It evolved under the same laws of gravity and nuclear physics and electromagnetism. Its galaxies contain the same types of stars. Its chemistry produces the same elements. Its planets form by the same processes. The hidden universe is not alien. It is more of the same in a volume so large that the 2 trillion galaxies we can see are a statistical rounding error. The map is radically incomplete, and what is off the map is not fundamentally different from what is on it. It is just forever inaccessible. The sphere you are at the center of. Right now, at this moment, you are sitting at the precise geometric center of the observable universe. Not approximately at the center, not near the center, at the exact center, by definition. And so is every other observer everywhere in the universe, regardless of where they are located. This is worth pausing on, because it sounds like either a philosophical statement about human specialness or a contradiction. It is neither. It is a direct consequence of how observation works in a universe with a finite age and a finite speed of light. The observable universe for any given observer is defined as the region from which light has had time to reach that observer since the universe began. Light travels at a fixed speed. The universe has a finite age. Multiply one by the other, and you get a maximum distance, and that distance is the same in every direction from every observer. Every observer is therefore at the center of their own observable sphere, a sphere of the same radius as ours, centered on their location rather than ours. An observer in a galaxy near the edge of our observable universe, a galaxy whose ancient light is just now arriving at our telescopes after 13 billion years of travel, has their own observable sphere. It extends 46.5 billion light-years in every direction from their location. It overlaps with ours in the region between us, and it extends into regions we cannot see in directions away from us. Their sky contains galaxies we will never observe. Our sky contains galaxies they will never observe. Each observable sphere is complete from the inside, a self-contained visible universe, while being simultaneously a tiny fraction of a much larger structure neither observer can access. This is the illusion of totality. the way a finite window onto a larger structure feels from inside the window, like the whole thing. If you have only ever been inside a single room of a large building, the room does not feel like a fraction of something larger. It feels like the space you inhabit. The room can be mapped, its distances measured, its contents catalogued. The building beyond it remains invisible, not because of any failure on your part, but because the walls of the room are opaque. The observable universe is our room. The walls are not matter. They are not opaque in any physical sense. They are a boundary drawn by the age of the universe and the speed of light, and reinforced by the inflation that pushed the rest of the building so far away that no signal from beyond it can reach us within the remaining history of the universe. By the time the photon arrives, its source is now 46.5 billion light-years away. The particle horizon is not where the universe began. It is where the most ancient photons currently reaching us originated, accounting for the expansion that has occurred since they set out. The particle horizon sits at 46.5 billion light-years because space has been expanding during the 13.8 billion years that light has been traveling. A photon emitted at the moment of last scattering, the moment the plasma cleared and photons became free, has been traveling for 13.8 billion years. But the source that emitted it has been carried away from us by the expansion during that entire transit time. The geometry of everything. There is an experiment that sounds impossible and is not. Drawing a triangle large enough to test the geometry of the universe. Not a triangle on Earth, not a triangle across the solar system, but a triangle so large that its sides are hundreds of millions of light-years long, and the question of whether its angles sum to 180 degrees, more than 180 degrees, or less than 180 degrees, encodes the global curvature of space. The cosmic microwave background provides the ruler for this measurement. In the early universe, before the plasma cleared, sound waves were propagating through the hot, dense medium. Pressure waves, driven by the competition between radiation pressure, pushing outward, and gravity, pulling inward. These waves had a characteristic scale, determined by how far sound could travel in the time available. Roughly the first 380,000 years of the universe's existence. When the plasma cleared and the background radiation was released, those sound waves froze in place, leaving an imprint on the temperature distribution of the background. Regions at maximum compression when the transition occurred appear slightly warmer. Regions at maximum expansion appear slightly cooler. The characteristic size of these features, set by the distance sound could travel before freezing, is known from basic physics to extraordinary precision. This frozen scale acts as a standard ruler. If you know the physical size of the ruler and you can measure the angle it subtends across the sky, you can calculate the geometry of the space between you and it. In a flat universe, a ruler of given physical size at a given distance subtends a specific angle. This is not an abstract result. It has consequences that propagate through every aspect of cosmology. A flat universe is one whose density equals the critical density exactly. It is one that inflated from an initial region with some starting curvature and was smoothed to apparent flatness by the inflationary expansion. It is one that, unless inflation stretched it to a genuinely infinite size, is vastly larger than the observable sphere. The measurement of flatness is simultaneously a measurement of structure we cannot see. In a positively curved universe, it appears larger because the curvature focuses light the way a magnifying glass does. In a negatively curved universe, it appears smaller. The measurement is direct. The conclusion is unambiguous. The Planck data places the first acoustic peak in the CMB power spectrum at an angular scale that matches the flat geometry prediction with extraordinary precision. The universe is flat. Independent confirmation comes from the pattern of galaxy clustering on the largest scales. The same frozen sound waves that imprinted on the temperature pattern of the CMB also left an imprint on the distribution of matter. As galaxies formed from the density fluctuations inflation seeded, they preferentially formed at separations corresponding to the characteristic scale of those early sound waves. This preferred separation, called the baryon acoustic oscillation scale, appears as an excess of galaxy pairs at a specific distance in large galaxy surveys. Measuring this scale across different distances allows the geometry of the universe to be inferred independently of the CMB. The result agrees with the CMB measurement. The universe is flat. The agreement between these two entirely independent lines of evidence is one of the most significant confirmations in modern cosmology. It is not possible to arrange this agreement through instrument error. The CMB measures photons from 13 billion years ago. Galaxy surveys measure the current distribution of matter. They are sensitive to different systematic effects, different foreground contaminations, different instrumental noise sources. Their agreement on the flatness of the universe is a genuine measurement of the geometry of space itself. Inflation's evidence in the data. Inflation is not merely a theoretical proposal invoked to solve the flatness problem. It makes specific, testable, quantitative predictions that have been confirmed by observation to a precision that is genuinely remarkable for a theory describing events occurring at 10 to the negative 36th seconds. The most important of these predictions concerns the spectrum of density fluctuations. Inflation produces fluctuations through the quantum mechanical behavior of the inflaton field. As the field slowly rolls down its potential energy landscape, quantum uncertainty means its value is not perfectly uniform. These quantum fluctuations are stretched to cosmic scales by the exponential expansion. When inflation ends and reheating converts the inflaton's energy into matter and radiation, these fluctuations become fluctuations in the density of the hot plasma. Regions of slightly higher density eventually collapse to form galaxies and clusters. Regions of slightly lower density become voids. The entire large-scale structure of the universe, every galaxy and filament and void in the cosmic web, grew from quantum fluctuations during inflation. The specific prediction is that these fluctuations should be nearly scale invariant, meaning they should have roughly the same amplitude at all scales, with a slight tilt toward less power at smaller scales. The tilt is characterized by a parameter called the spectral index. Simple inflationary models predict a spectral index slightly less than 1. The Planck measurement returned a spectral index of 0.9649 plus or minus 0.0042. The prediction of a value slightly below 1 is confirmed. The agreement is not approximate. It is a specific quantitative prediction from a theory of events 13 billion years in the past, confirmed by measurement to within a few tenths of a percent. The agreement between inflation's predictions and the observed properties of the CMB is the primary reason cosmologists take inflation seriously. It is not a philosophical argument or an aesthetic preference. It is a quantitative theory making quantitative predictions that are quantitatively confirmed. The mechanism that solved the flatness problem is also the mechanism that correctly predicted the statistical properties of the oldest light in the universe. These two facts are related. They are consequences of the same physics, and that physics, applied consistently, guarantees that most of the universe is beyond our reach. Dark energy and the shrinking window. Everything we have discussed so far has treated the boundary of the observable universe as a fixed fact. The particle horizon sits at 46.5 billion light-years. The actual universe is at least 251 times larger. These numbers are determined by the age of the universe and the history of inflation. They are not changing. But there is a second boundary that is changing, and it is changing in a direction that makes the problem of the hidden universe worse with every year that passes. It is called the cosmic event horizon, and it sits at approximately 16 billion light-years. The event horizon is not the boundary of what we can see. It is the boundary of what we can ever interact with. It is defined by the accelerating expansion of space, driven by dark energy. If you send a signal today toward an object currently at the event horizon, that signal will just barely reach the object's location as the object recedes away. If you send a signal toward an object beyond the event horizon, the expansion of space will carry the destination away faster than your signal can travel, and the signal will never arrive. The event horizon is the boundary beyond which the universe and everything in it is already effectively lost to us, even though we can still see it, because the light we see from it left long ago, and nothing we can ever do will allow us to send or receive any new information from it. Dark energy is what drives the accelerating expansion that creates this horizon. Its discovery in 1998 by two independent teams measuring the apparent brightness of Type 1a supernova and finding them dimmer than expected. Dimmer meaning farther. Farther meaning the expansion was faster in the recent past than it should have been, if only gravity were acting, was genuinely shocking. The universe was not just expanding, it was accelerating. Something was overcoming gravity on the largest scales and pushing everything apart faster and faster. That something is given the name dark energy, a label that conveys accurately how much we do not understand it. The most straightforward model identifies dark energy with the energy density of the vacuum, a cosmological constant in Einstein's equations. In this model, the energy density of dark energy remains constant as the universe expands, unlike matter and radiation, which dilute as volume increases. This constant energy density exerts a kind of negative pressure on the geometry of space-time that produces the observed acceleration. The cosmological constant model fits the available data well, but it comes with a theoretical problem of alarming severity. Quantum field theory, the framework that correctly predicts the properties of particles and forces to 11 decimal places, predicts a value for the vacuum energy that is approximately 120 orders of magnitude larger than the observed value of dark energy. Not 20 times larger, not 1,000,000 times larger, 120 orders of magnitude larger. The discrepancy between the theoretical prediction and the measured value is the largest in the history of physics. Something is canceling the predicted vacuum energy to extraordinary precision, leaving only the tiny residue we observe, and no one knows what that something is. The cosmological constant model fits the available data well, but it comes with a theoretical problem of alarming severity. Quantum field theory, the framework that correctly predicts the properties of particles and forces to 11 decimal places, predicts a value for the vacuum energy that is approximately 120 orders of magnitude larger than the observed value of dark energy. Not 20 times larger, not 1,000,000 times larger, 120 orders of magnitude larger. The discrepancy between the theoretical prediction and the measured value is the largest in the history of physics. Something is canceling the predicted vacuum energy to extraordinary precision, leaving only the tiny residue we observe. And no one knows what that something is. The structural parallel between the cosmological constant problem and the flatness problem is worth noting. Both involve precision that seems impossibly extreme. The flatness problem asks why the initial density of the universe was tuned to 1 part in 10 to the 62nd. The cosmological constant problem asks why the vacuum energy is tuned to 1 part in 10 to the 120th relative to the theoretical prediction. In both cases, the answer we have found involves inflation. Inflation solves the flatness problem by erasing its dependence on initial conditions. The cosmological constant problem has no analogous solution that commands broad acceptance. It remains open in a way that suggests something fundamental is missing from our understanding of the relationship between quantum mechanics and gravity. Some theorists have proposed that the cosmological constant problem is solved anthropically. In a multiverse of pocket universes with different vacuum energies, only universes with vacuum energies small enough to permit structure formation can contain observers. The observed value of dark energy, while seeming unnaturally small by theoretical standards, is roughly the largest value consistent with the formation of galaxies, and therefore with the existence of observers to measure it. This is not an explanation in the traditional sense. It is a selection effect. But in a multiverse, selection effects are the only available explanations for values that vary from pocket to pocket. Whether this constitutes genuine physical understanding or a retreat from explanation is one of the deepest unresolved debates in the philosophy of physics. The implications of dark energy for the future of the observable universe are stark. The event horizon at 16 billion light-years is currently shrinking in co-moving coordinates. Galaxies that are today just inside the horizon will, over the coming billions of years, drift beyond it, as the accelerating expansion carries them across the causal boundary. The set of objects we can ever interact with is not growing, it is contracting. In roughly 100 billion years, the sky as seen from the Milky Way will contain only the galaxies of the local group, gravitationally bound together against the expansion. Everything beyond them will have been pushed beyond the event horizon, their light redshifted to wavelengths too long for any instrument to detect. The evidence that 2 trillion galaxies once filled the observable sky will be gone. Astronomers of that distant era, if any exist, will look out into a universe that appears to contain only their own galaxy surrounded by dark emptiness, with no way of knowing from observation alone that the universe ever contained anything beyond it. The topology question. We are living at the moment of maximum observable richness. The sky contains more information right now than it will ever contain again. The window is open. It is closing. Everything we have discussed so far assumes that space beyond the observable sphere simply continues. More of the same geometry, more of the same physics, extending outward in every direction without limit. This is the default assumption. the simplest extrapolation from local observations. But it is not the only possibility. There is another class of models that does not require the universe to be infinite and does not require it to have an edge. And the distinction between these models and the standard picture is genuinely important for understanding what the hidden universe might be. The distinction is between geometry and topology. These words are often used interchangeably in casual conversation, but they describe entirely different things. Geometry is local. It describes the curvature of space in any particular region, the rules that govern distances and angles near any given point. Topology is global. It describes how the space is connected at the largest scales, how regions relate to each other across vast distances that no local measurement can capture. The same local geometry can correspond to many different global topologies. A flat surface can be an infinite plane, but it can also be a torus, the surface of a donut, which is locally flat at every point, but globally connected back on itself. If you lived on a flat torus and drew a small triangle, its angles would sum to 180 degrees exactly, just as on a flat plane. You could not distinguish between the two geometries from local measurements alone, but if you traveled far enough in a straight line on the torus, you would eventually arrive back where you started. The space is finite. It has no boundary, no edge, no point where space stops, but it loops back on itself in a way that makes it finite in total volume. The three-dimensional analog is called a three-torus. Imagine a cube in which the left face is identified with the right face, the top face with the bottom face, the front face with the back face. Walk through one wall and you emerge from the opposite wall. The space is locally flat and globally connected. It is finite in total volume without having any edge or boundary. And the Planck measurements showing flatness are entirely consistent with this topology, provided the identification scale, the distance at which the space loops back on itself, is larger than our observable sphere. If the universe has a toroidal or other non-trivial topology, there's a specific observational signature: matched circles in the cosmic microwave background. If space loops back on itself at a scale smaller than the observable sphere, we would be seeing the same region of early universe plasma from multiple directions. The temperature pattern on one circle of the sky would exactly match the pattern on a corresponding circle on the opposite side. The Planck satellite searched for these matched circles systematically. It did not find them. This rules out a small toroidal universe, where the loops are shorter than the diameter of the observable sphere. But if the loops are longer than the observable sphere, as inflation would likely guarantee, the signatures are beyond our view. A large toroidal universe is entirely consistent with all current observations. There are more exotic topological possibilities. A Picard horn is a three-dimensional space with finite volume but infinite extent in one direction, shaped roughly like an infinite trumpet. The specific mathematical properties of this geometry produce distinctive signatures in the low multipole structure of the CMB temperature pattern, signatures that some researchers have associated with the observed anomalous low power at large angular scales in the Planck data. The evidence is not strong enough to constitute a detection, but the anomaly is persistent, and the topology models are not ruled out. The shape of the universe is an open question, not in the sense of lacking a definite answer that observations could in principle provide, but in the sense that the answer may be observationally inaccessible. If the topology identification scale is beyond our particle horizon, we cannot see the matched circles. We cannot distinguish a topologically non-trivial universe from an infinite flat one. The shape of space may be permanently hidden from us by the same causal boundary that hides most of the universe's content. The eternal inflation fracture. There is a consequence of inflationary theory that most popular accounts mention briefly and then move past, as though it were a colorful footnote to the main story rather than one of the most radical proposals in the history of science. It is called eternal inflation, and once you follow it to its conclusion, the universe you thought you lived in fractures into something almost unrecognizable. The mechanism of inflation involves a quantum field, generically called the inflaton, rolling slowly down its potential energy landscape, while its high energy density drives exponential expansion. The classical picture is simple. The field starts high, rolls slowly. Inflation occurs, the field reaches the bottom, inflation ends. Reheating converts the field's energy into matter and radiation. The hot Big Bang begins, clean and finite. Our universe emerges from one inflationary episode that starts and stops. But quantum mechanics does not permit clean and finite processes. Quantum fields fluctuate. The uncertainty principle guarantees that no quantum field can be perfectly uniform. As the inflaton rolls classically downhill, quantum fluctuations continuously nudge it up and down around the classical trajectory. In most regions, the classical rolling dominates, and inflation ends on schedule. But in some regions, purely by chance, the quantum kick is large enough to push the field back up the potential hill, reversing the classical roll locally. In those regions, inflation does not end. It continues. Here is why this matters. Inflation is exponential. Space is doubling in volume on extremely short timescales. New volume is being created at an exponential rate, even if the probability of a quantum kick sufficient to continue inflation is very small in any given region. The exponentially growing volume means that the total volume in which inflation is continuing grows faster than the volume in which it is ending. Inflation, once started, does not stop globally. It ends in isolated pockets while continuing everywhere else. It is, by the mathematics, eternal. Andre Linde worked out these consequences in detail in the mid-1980s. Each pocket of ended inflation becomes a hot Big Bang, a local universe. Our observable universe is one such pocket. But surrounding our pocket, inflation is still occurring. Other pockets are forming constantly, each one a potential universe with its own Big Bang, its own period of cooling and structure formation. The eternally inflating background produces an endless succession of pocket universes, each one causally disconnected from every other. Not separated by any finite distance, but separated by a background of still inflating space that will always expand faster than any signal can cross it. The separation is not spatial, it is causal. The pocket universes are not in each other's futures or pasts. They are genuinely disconnected. If each pocket universe that forms inherits its physical constants from the state of the inflaton field at the moment, inflation ends in that pocket. And if the inflaton field can settle into different vacuum states, then different pocket universes may have different physics, different values of the fine structure constant, different electron masses, different strengths of the nuclear forces, different values of the cosmological constant. String theory, the leading candidate for a quantum theory of gravity, predicts an enormous number of possible vacuum states, estimated at around 10 to the 500th. Each state corresponds to a different set of physical constants. In the eternal inflation picture, pocket universes sampling this landscape would produce an enormous variety of universes, most with physics that does not permit complexity, a few with physics close enough to ours to permit stars and chemistry and observers. This is not a speculation invented to make the universe seem more interesting. It is a logical consequence of the quantum mechanics that inflation requires to produce the density fluctuations we actually measure. The fluctuations we see in the CMB are there because the inflaton field fluctuated. The same fluctuations that produce our CMB also, in some regions, push the field back up the potential and continue inflation. The multiverse is not an add-on. It is entailed by the physics that explains what we observe. Whether it is science in the conventional sense is a genuine question. A prediction that no possible observation can confirm or refute raises uncomfortable issues about the boundary between theoretical physics and unfalsifiable speculation. But the discomfort does not make the argument go away. The equations do not stop at the edge of our observable sphere. They continue beyond it, and what they describe beyond it is a structure vastly larger and more varied than the already staggering 2 trillion galaxy universe we can observe. The anomalies at the edge, the cosmic microwave background, has been measured with extraordinary precision. It has been mapped by 3 generations of satellite instruments, analyzed by hundreds of independent research teams, tested against the predictions of the standard cosmological model using every statistical tool available. The agreement between theory and observation is, on most scales, remarkable. The acoustic peaks sit exactly where flat geometry with inflation-seeded perturbations predicts. The spectral index is precisely as expected. The polarization pattern is consistent with the temperature pattern in the ways the physics demands. But the agreement is not complete. There are anomalies, small, persistent, well-documented anomalies that appear in both WMAP and Planck data that survive multiple independent analysis methods that remain after every known foreground contamination has been carefully removed. They are not large enough to overturn the standard model. They are not statistically conclusive enough to claim as discoveries. But they have not gone away with better data. And in science, the anomalies that do not go away tend to be the ones worth watching. The CMB cold spot is the most extensively discussed. Located in the southern sky in the direction of the constellation Eridanus, it is a region roughly 5 degrees across that is significantly colder than the standard model of inflationary fluctuations predicts it should be. The probability of such a feature occurring by chance in a purely random primordial fluctuation field has been estimated between 1 and 2%. The leading explanation is a supervoid, a large underdense region along the line of sight whose gravitational potential produces an integrated Sachs-Wolf effect that cools photons as they climb out of it. Galaxy surveys have found evidence for an underdense region in that direction, but the supervoid alone does not fully account for the temperature deficit. The cold spot remains slightly colder than the supervoid can explain. An alternative explanation is a bubble collision signature. If eternal inflation is correct and our universe is a pocket formed by the end of inflation in a local region, other pocket universes are forming nearby in the inflationary background. Under certain geometric conditions, 2 expanding bubbles can collide. A collision would deposit energy asymmetrically into the CMB of each bubble, creating a circular region of anomalous temperature with a distinctive profile. The bubble collision hypothesis is not confirmed. The cold spot's profile does not perfectly match the predicted signature, but it has not been definitively ruled out either. The standard explanation is foreground contamination. Emission from within the solar system or from the plane of the Milky Way, if not perfectly removed, could correlate with the ecliptic. Cosmologists have worked extensively to clean these foregrounds using multiple independent methods. The anomaly persists after the cleaning. It is reduced, but it does not disappear. Whether what remains is a systematic artifact of foreground removal or a genuine feature of the primordial CMB is unresolved. The axis of evil is a different kind of anomaly. It refers to the alignment between the quadrupole and octopole, the two largest scale temperature variations in the CMB. In a universe whose primordial fluctuations are generated by inflation, which is isotropic with no preferred direction, these two components should point in random, independent directions. They do not. The Planck data shows that they are aligned with each other to a statistically improbable degree. More striking, both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sun. This correlation between the largest scale structure of the universe and the geometry of our local solar system is deeply unexpected in a standard isotropic cosmology. The probability of this alignment occurring by chance is less than 1%. The axis of evil is a different kind of anomaly. It refers to the alignment between the quadrupole and octopole, the two largest scale temperature variations in the CMB. In a universe whose primordial fluctuations are generated by inflation, which is isotropic with no preferred direction, these two components should point in random, independent directions. They do not. The Planck data shows that they are aligned with each other to a statistically improbable degree. More striking, both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sun. This correlation between the largest scale structure of the universe and the geometry of our local solar system is deeply unexpected in a standard isotropic cosmology. The probability of this alignment occurring by chance is less than 1%. The quasar-dipole anomaly adds a third independent line of evidence. The distribution of quasars across the sky, very distant active galactic nuclei visible across cosmological distances, should show a dipole signal from our motion through the universe, exactly aligned with and proportional to the dipole in the CMB. A study using the Catwise catalog of infrared sources found a quasar dipole approximately 4 standard deviations larger than the CMB dipole predicts. 4 sigma is not a statistical fluctuation. It is a significant mismatch between the predicted and observed large-scale structure of the universe. If the mismatch is not a systematic effect in the catalog, it implies a genuine, large-scale anisotropy in the distribution of matter at the largest scales, a violation of the cosmological principle that the universe is statistically the same in every direction. None of these anomalies has crossed the 5 sigma threshold for a discovery claim. The history of physics contains many 3 sigma anomalies that disappeared with more data, but it also contains cases where persistent small anomalies were the first indications of genuinely new physics. The anomalies at the edge of the CMB are worth watching, not because they individually demand a radical explanation, but because their persistence across independent datasets and analysis methods suggests they are telling us something. The universe may be leaving fingerprints inside our bubble of processes occurring beyond the boundary of what we can directly observe. The instruments we are building. The picture of the hidden universe is not static. It is being refined continuously by observations that push to greater precision, larger scales, and earlier cosmic times. The instruments being deployed and planned over the next decade will sharpen every aspect of what we know about the observable universe, and by inference about what lies beyond it. Next generation CMB experiments, including the Simons Observatory and the proposed CMBS-4, are targeting the B-mode polarization signal that would indicate primordial gravitational waves from inflation. Detection would directly measure the energy scale of the inflationary epoch and constrain the range of viable inflationary models. Non-detection at the sensitivity these experiments will reach would rule out a broad class of high-energy inflation models and significantly narrow the theoretical landscape. The Dark Energy Spectroscopic Instrument, DESI, is building the largest three-dimensional map of the universe ever assembled, measuring spectroscopic redshifts for tens of millions of galaxies to trace the baryon acoustic oscillation scale across cosmic time. Its first-year data, released in 2024, showed hints that the dark energy equation of state parameter may not be constant, that dark energy may be dynamical rather than a cosmological constant. The statistical significance was not sufficient for a detection claim, but the hint was consistent across multiple independent analysis methods. Subsequent data releases will clarify whether the signal grows or dissolves. And the LISA Gravitational Wave Observatory, planned for launch in the 2030s, will open a new frequency window on the gravitational wave sky, sensitive to the mergers of massive black holes at the centers of galaxies and to a possible gravitational wave background from the early universe, including potential signals from the inflationary epoch itself. If the energy scale of inflation was high enough, the primordial gravitational wave background may be detectable by LISA, providing a direct probe of conditions in the universe at 10 to the negative 32nd seconds. All of these instruments are measuring the observable universe. They cannot directly observe what lies beyond the particle horizon, but they constrain the physics that governs what is beyond it. The same equations that describe the CMB fluctuations describe the structure of the hidden universe. The same dark energy that is currently shrinking the event horizon determines how much more of the universe will be lost to us over cosmic time. Better measurements of what is inside the bubble tell us more about what is outside it, even if they cannot make the outside directly visible. The wall was there from the beginning. Let us step back from all of it. From the flatness problem and the knife-edge precision of 1 part in 10 to the 62nd power. From inflation and the factor of 10 to the 26th that it applied to space in an interval so brief that no human unit of time contains it comfortably. From the 2 trillion galaxies and the 15 million times that number that the Vardanyan analysis implies sit beyond our horizon. From the topology question and the toroidal universe that would loop back on itself at scales we cannot probe. From eternal inflation and the pocket universe foam it produces. From the anomalies in the CMB that may or may not be fingerprints of physics beyond the boundary. From dark energy and its patient work of pushing more of the cosmos beyond causal reach with every year that passes. Step back from all of it and look at what the pieces add up to, because they do not form a collection of independent puzzles. They form a single story and the story is about something more specific than the mere size of the universe. It is about why the structure of reality is organized the way it is, and why the physics that made the observable universe what it is also guaranteed that most of reality would be permanently beyond our reach. The flatness problem is the beginning of the thread. The universe is flat to one part in 10 to the 62nd at the Planck time. This precision is not a gift, it is a crisis. No mechanism within classical Big Bang cosmology can produce it without simply assuming it as an initial condition, which is no explanation at all. The crisis demands a solution. Inflation is the solution. It takes whatever curvature the universe started with and dilutes it below the threshold of detection by stretching space exponentially. It explains the flatness without requiring fine-tuned initial conditions. It solves the horizon problem and the monopole problem with the same mechanism. And its specific quantitative predictions about the spectrum of primordial density fluctuations are confirmed by the Planck measurements to within a fraction of a percent. But inflation, applied consistently, does not stop solving problems at the edge of the observable sphere. It keeps going. The same exponential expansion that smoothed our observable patch also pushed everything that was in causal contact with our region beyond the distance any signal can cross. The same quantum fluctuations that became the CMB temperature pattern also, in some regions, sustained inflation past the moment it ended in our pocket. The same physics that produced the observable universe produced an unobservable one vastly larger, populated by the same laws and structures, permanently beyond reach. The hidden universe is not separate from the observable one. It is produced by the same event, the same inflationary epoch, the same quantum mechanics. Our observable sphere is not a complete object. It is a fragment of a larger structure from which it has been causally severed. The severing is not a border like a national boundary, a line drawn on a map with something different on each side. It is a causal horizon, a limit on which events can have influenced which other events, built into the structure of space-time by the speed of light and the expansion history of the universe. And the severing is permanent. It does not close with time. The event horizon is shrinking. The fraction of the universe we can interact with is decreasing. We are not approaching a moment of complete knowledge. We are living in the era of maximum access, and the access is diminishing. The observer and the boundary were created together. The inflation that made the universe habitable, flat enough and smooth enough for structure to form, cool enough for atoms and stars and chemistry, is the same inflation that drew the horizon beyond which structure remains forever invisible. Our existence and our ignorance are consequences of one event, seen from different angles. The physics that built us also guaranteed what we cannot see, and yet something remarkable follows from this. We know it. We can calculate the minimum size of what we cannot see. We can place a lower bound on the number of hidden galaxies. We can derive, from measurements made inside the observable sphere, the properties of the physics that governs the unobservable one. The Planck measurements do not just tell us the universe is flat. They tell us that at least 15 million observable universes worth of structure must lie beyond our horizon. This is inference, not observation, but inference from the most precise cosmological measurements ever made, applied through equations that have been confirmed to extraordinary precision wherever they can be tested. The universe has not given us access to most of itself, but it has given us the physics to infer what we cannot see, and the physics, followed wherever the equations lead, describes a structure so large that the 2 trillion galaxies of the observable sky are a statistical rounding error within it, a structure produced by the same laws that produced us, a structure that will never, by any physical means, reveal itself directly to any observer anywhere inside the observable sphere. The wall is not a wall in the physical sense. There is no membrane. There is no change in the character of space at the particle horizon. Galaxies beyond it are not frozen or absent or different. They exist, governed by the same physics, forming the same structures, running through the same cosmic history. The boundary is in the causal relationship between those regions and us, not in the regions themselves. The observable universe, 46.5 billion light-years in radius, 2 trillion galaxies, the most complex structure we have ever had the tools to study, is a window. It is a small window. It is a bounded window. Its boundary is enforced by physics rather than technology, which means no future telescope will move it. It is also a closing window, as dark energy continues its work of pushing more of the cosmos beyond the event horizon, reducing the set of objects with which we can ever exchange information. The boundary is made of causality, of the finite speed of light operating in a universe that expanded faster than light can cross during the inflationary epoch, and that is currently accelerating under dark energy. Causality in a relativistic universe is not a suggestion. It is the structure within which all physical law operates, and a causal boundary of this kind is not a temporary limitation. It is a permanent feature of what it means to exist inside a space-time with this history. The universe did not grow too large to see by accident. It grew in a way that was intrinsic to the physics that made it habitable. The same epoch that smoothed space and seeded structure and created the conditions for stars and planets and observers drew the horizon those observers can never cross. The 2 facts are not independent. They are aspects of a single physical process. And understanding that process, following its mathematics wherever it leads, is what cosmology has been doing since the first measurements of the CMB were made. The observable universe is a consequence. The hiddenness is a consequence. The 2 trillion galaxies we can see, and the 32 sextillion we cannot, are all consequences of the same inflationary physics, operating in the same way in the same early universe, producing visible structure in one fraction and invisible structure in the rest. But it is still a window, and what we can read from inside it, through the CMB and the galaxy surveys and the gravitational wave detectors and the spectroscopic maps, describes a universe whose true extent dwarfs anything we can observe. The equations do not end at the boundary. They continue beyond it, describing physics operating in regions we will never see, producing structures we will never catalog, running through histories we will never read. We are those instruments. We are the universe's means of reading its own observable fragment and inferring its hidden remainder. The inference tells us more about what we cannot see than we have any right to expect, given the smallness of the window. And the window, bounded as it is still open. For now, you have been watching the entire history of the universe. Do not forget to like and subscribe and leave a comment telling us what you think. Thanks for watching, and we will see you next time.